Having looked at the combustion process in both SI and C engines, the next important topic which we are going to discuss is that of how do we first of all determine what is the correct proportion of fuel and air that needs to be introduced into the engine, and second, how do we realize the introduction of this fuel air mixture into the engine, right, depending on the operating condition of the same. Okay. So, we are going to discuss the topic which is called as mixture preparation. Let us consider SI engines. So, let us look at mixture preparation in SI engines. So, and what are the different factors that affect the same, and also like how the mixture is introduced, right. So, we will look at those concepts. So, in general, the term carburation is used to refer to this process of preparing the appropriate fuel air mixture, okay, in an engine. So, what is carburation? It is nothing but the process of forming a combustible fuel air mixture by mixing the proper amount of fuel with air before admission of the same, right, of the mixture into the combustion chamber. So, that is what is called as a process of carburation, okay. And a device used for achieving this carburation in general is what is called as a carburetor, okay. But we will see that there are many devices now which are used to prepare this mixture, okay. But in general, okay, this is a general term. A carburetor is a device used for carburation, okay. So, carburation is a process, okay. So, now let us look at what are all the factors that affect carburation and discuss them. So, the first factor which we would consider is engine speed, okay. So, let us say we have a 4-stroke engine. So, I think if I remember correctly, we have done this calculation before. Let us say the engine is rotating at 1500 rpm. This calculation was a similar calculation, right. What is the time available for the suction stroke if the engine is rotating at 1500 rpm? If it is 1500 rpm, that means that how many revolutions per second divided by 60, it will give me 25 revolutions per second. So, 25 revolutions per second means one revolution will be how many milliseconds? 1 by 25, which will be 40 milliseconds. So, in a 4-stroke engine, one revolution would that is one cycle is completed in 2 revolutions of the crankshaft, right. So, that means that we would have around 20 milliseconds for each stroke, including the suction stroke on an average, okay. So, on an average we are going to have 20 milliseconds. Now, the same engine speed is increased to 3000 rpm, let us say we double it. So, what should happen to this time? On an average we are going to have 10 milliseconds for each stroke. So, consequently what is it that we can observe? if I increase the engine speed, the time available for the carburation process decreases, right. So, the time available for introducing the fuel air mixture decreases. So, any system that essentially does this operation should factor this one, right. So, this is an important factor to consider. So, we can immediately observe that higher the engine speed, lower is the time available for charge induction. Okay. So, as we recall, the term charge is also used in this context to denote a fuel air mixture, right. So, that is what it is. Okay. So, that is important. Okay. So, that is one factor which is important, engine speed. So, the next factor which is also important are the vaporization characteristics of the fuel. So, please note that if I want to prepare a combustible and homogeneous fuel air mixture in a spark ignition engine, already we have discussed that there are two attributes which are important for any combustion process, right. So, that is involving this fuel and air, right, in engines. Please recall again, for combustion we need hydrocarbon, that is fuel, we need oxygen in the correct proportion, and we need a mechanism for initiating the combustion. But when I introduce the fuel and mix it with air, as we have already discussed, the fuel should first atomize, that means that we should break larger droplets of fuel into finer particles, and then those particles should vaporize and mix with air. Okay, then only we will get a nice homogeneous mixture of fuel and air in the combustion chamber, correct. So, the vaporization characteristics of the fuel become very important, okay, when we look at the process of carburation. Okay. So, in that regard, the temperature of the incoming air also becomes important, right. So, in general, right, why? Because higher the temperature, better is the or quicker is the vaporization process, right, because if I want to go from the liquid form to the vapor form, I need to provide the fuel with the corresponding latent heat, right, corresponding to the fuel latent heat of vaporization, right, to go from the liquid form to the vapor state, correct. So, if I increase the temperature of incoming air, better is going to be the vaporization process. But what is one what to say limitation with this? As we already discussed, if we increase the temperature of incoming air, in SI engines the chances of knocking may also increase, the tendency for knocking also may increase, and also the volumetric efficiency would also decrease, right, as we have already discussed. You know, like if we increase the temperature of the incoming air even slightly, the density of the incoming air would decrease. Then for the same volume I am going to take in lesser amount of charge, right, in the combustion chamber, right. So, that is going to decrease the volumetric ratio. So, if you look at the temperature of incoming air, increasing it would lead to better or improved vaporization and mixing. However, in addition to that, is even if we ensure that knocking is avoided with a small increase in temperature, okay, the volumetric efficiency would be affected. Okay, so we have to balance all these factors. Okay, so when we look at this one as well. Of course, the design of the device itself, like plays a big role, as we will see. Okay, so depending on various philosophies and methods, the actual instrument or device itself is designed carefully. Okay, so that's something we will look at, like as we go along. Okay, now the question becomes, okay, so these are the factors affecting carburation. So depending on the operating condition of the engine and the position of the throttle, what is the composition of the mixture that we want? See, because we have already seen that there is something called as the chemically correct mixture or the stoichiometric fuel air mixture, and there is a rich mixture that has more fuel than the chemically correct mixture, and a lean mixture which has less fuel than the chemically correct mixture. So depending on the operating condition of the vehicle, see, what do I mean by operating condition of the vehicle? If I am starting from rest and accelerating, what is the type of mixture which I would require? Okay, if I am cruising at high speeds, let us say on a highway, right, what is the type of mixture I want to have? Suppose while cruising I want to overtake another vehicle, so then what is the type of mixture that I would once again require, right. So those are important questions to ask. Okay, so that's where even like the type of mixture requirements also come in, right. So what do we expect the mixture to be, right, qualitatively, right, for various operating conditions. So if you want to look at it in a qualitative manner, right, so what is it that we want? So if we look at the air fuel mixture itself, okay, so considering the air fuel mixture and the air fuel ratio, we can immediately see that in this diagram, it is once again a qualitative diagram. Okay, so this is a plot of the air fuel ratio, okay, is given against the power output from the engine and the BSFC. Please recall that BSFC stands for brake specific fuel consumption. Of course, ideally I would want the BSFC to be as small as possible, right, that would lead to better fuel economy obviously, right. So if you look at the stoichiometric mixture, so this vertical line indicates the chemically correct air fuel ratio. So we already know that to the left of this we have a rich mixture, to the right of this we have a lean mixture, because we are plotting air fuel ratio, right. Air fuel ratio lower than the stoichiometric ratio implies a rich fuel air mixture and vice versa, right, for a lean mixture. So if I want to get the best power, like we would typically require a rich mixture, right, because I would want to get more energy output from the engine, right. So I would want to burn more fuel, right, and essentially get more energy output, okay, from the engine. So typically for high power output, we would want a rich mixture. See, for example, when would I want to have a high power output in the scenario that we just discussed? Suppose let us say I am cruising on a highway, right, and I want to overtake a vehicle. So what is it that we typically do? We are already in the highest gear. What we will do is that, like, we will press the accelerator pedal or throttle pedal a little bit more, and then we expect the corresponding energy to be given to the car to overtake the vehicle in front of us, right, in another lane, right. So essentially we would do that. Then in order to get that process done, I should introduce a rich mixture in the cylinder. Okay, this is one scenario. Okay, we will also see where a rich mixture is required under other operating conditions. So for best fuel economy, okay, or mileage, okay, A lean mixture is obviously preferred, right. So, and that is what happens when we are cruising. Okay. So, typically when we reach to what are called cruising speeds in a typical car, right, or a typical vehicle, and we are essentially going at that constant speed on a highway, like we would typically want to operate around this region, okay, where our BSFC is low, okay. And when we come to transmission, we will also relate all these points to the overall vehicle requirements also, okay. We will discuss what are the traction forces requirements of a typical automobile road vehicle, and we will correlate all these operating conditions to the gearbox and the vehicle traction requirements, okay. We complete the process or complete the discussion when we discuss transmission also. So, I would come back when we do the discussion on transmission, okay. So, we can see that a carburetor also needs to factor this one in, right, because it needs to vary the air fuel ratio such that depending on the requirement of the vehicle, the air fuel ratio needs to be varied in a range, okay. So, a carburetor must be able to meet varying air to fuel ratio requirements, okay, depending on the operating conditions of the vehicle, okay, and the engine, okay. So, one needs to see that one can immediately realize that we need the device to have this capability, okay, to vary the air fuel ratio, okay, depending on the requirements. And typically how does the driver convey these requirements? Suppose let us imagine that we are driving a car, right, or a two-wheeler, whatever vehicle we want to consider, right. How would we convey the requirements to the engine? By pressing the throttle pedal, right, in a car, or in a two-wheeler, in a motorcycle, we essentially rotate the throttle, right, which is a hand actuator, right. So, essentially we are displacing the throttle pedal, right, in a typical car, let us say, okay. So, that displacement of the throttle pedal results in displacement opening of what is called as a throttle valve, okay. We will look at it in the next class, okay. So, but the important thing is the following. So, depending on where the throttle position is, one needs a varying what to say mixture, okay. So, what do we mean by that, right. So, let us look at this curve. So, in this curve you see that we have throttle opening on the abscissa, right, and fuel air ratio, not air fuel ratio, okay. It is just the reverse of that, inverse of air fuel ratio, it is the fuel air ratio, okay. So, higher fuel air ratio than stoichiometric means it is a rich mixture, alright, please remember that. So, fuel air ratio in the ordinate, okay, or the vertical axis. So, now we can immediately observe that the throttle opening goes from, that is nearly 0, that is when you do not press the accelerator pedal, you have a very small throttle opening, to flooring the accelerator pedal. So, we can see that the mapping of the fuel air ratio versus the throttle opening in general, in a qualitative sense, follows this profile, okay, which is given by A, B, C, D, okay. So, at low throttle openings we can immediately see that low throttle opening on low and high throttle opening, we can immediately see that we require a rich mixture, right. I am sure all of us can observe that. Okay, so let us say the stoichiometric mixture is somewhere here. Okay, so that is the stoichiometric ratio. Okay. On the other hand, when we go for mid range throttle opening, typically we prefer a lean mixture. The question is why, right? Why would one want to have a rich mixture at low and high throttle openings and typically a lean mixture in the mid range throttle opening? Okay. So, we will discuss this in the next class along with what we expect from the vehicle when we press the throttle, as where we control the opening of this throttle valve. Okay. So, let us continue the discussion in the next class. Thank you.